Right, so let's take a look at first section in chapter 2, which is section 2.1. And in this chapter, basically what we're going to do is look at polynomials. Okay, so we'll do a lot of stuff on the calculator, looking at polynomials, and then we'll also do a little bit of stuff algebraically. All right, so first thing is let's take a look at this graph. All right, and just type it in and see what it looks like. Okay, 2x cubed minus 3x squared minus 3x squared minus 3x plus 2. Okay, and before I even graph it, okay, what I want to do is just kind of look at the highest exponent in this equation. Okay, it happens to be on the first term, and the highest exponent is a 3. Well, that 3 tells us a little bit about the graph. Okay, for a polynomial, the highest exponent tells us how many times that graph could cross the x-axis. Okay, it doesn't guarantee it's going to cross that many times, but it's an upper limit. It tells us a maximum number of times that this graph could cross the x-axis. All right, so let's take a look at our graph. And you know what? Let's do zoom 6. Get a better window on that. Okay, and in this case, we can see that it does cross 3 times. Okay, so that's our first question. How many times does this graph cross the x-axis? 3 times. All right. Next thing I want you to take a look at is how many times that graph turns. All right, if we look at it, we can see that it's turning twice. Okay, once right about there, and then once right about there. All right, so if you look at that highest exponent and you take 1 away from it, so in this case the highest exponent is 3, take 1 away from it, you get 2. That tells us how many times the graph could turn, so up to 2 times. Okay, next thing, what is the y-coordinate where the y-coordinate of the point where the graph crosses the x-axis? Okay, so what I'm basically looking for is what would be the y value of this point, and that point. Well, if you look at that point, okay, all 3 of those points, they're all on the x-axis. Okay? Any point that's on the x-axis, you haven't gone up, you haven't gone down at all. So your y value of a point, if you haven't gone up and you haven't gone down, is 0. So that's the y-coordinate for all those points. All right. Next thing I want to do is show that what I have written here, x plus 1 times 2x minus 1 times x minus 2 is equivalent to the function f of x I have up above. Now, one way you might think we could do that is just to graph it. Okay, if we graph what I have in those 3 sets of parentheses, okay, and then we graph what we have up above, if the 2 graphs look the same, you might say, oh, well, they're the same. But really, a graph is not a way to actually prove 2 things are the same. Okay, the only way we can do that is to actually use our distributive property and do it out. Okay, so let's do it out for the first 2 sets of parentheses. We're going to get x times 2x is 2x squared. X times negative 1 is negative x. 1 times 2x is 2x. And 1 times negative 1 is negative 1. Okay, we'll combine our like terms and then distribute that out to x minus 2. All right, so we're going to get 2x squared plus x minus 1 times x minus 2. All right, now we'll distribute one more time. Okay, 2x squared times x is 2x cubed. 2x squared times negative 2 is negative 4x squared. Now we'll distribute the x. X times x is x squared. X times negative 2 is negative 2x. Negative 1 times x is negative x. And negative 1 times negative 2 is plus 2. Okay, let's combine our like terms and see what we get. So we get 2x cubed. We have minus 4x squared plus x squared. So that's a minus, oops. That's going to be minus 3x squared. Okay, let's make sure that's what we had up above. Yep. All right, and then we've got minus 2x minus x, which gives us minus 3x. And our last step is plus 2. So that does match what we have up above. All right, so as we can see, by distributing it out what we had, okay, this expression is exactly the same as what we had up above. So we just proved that they're equivalent. All right, now, last thing I want to do is actually find all the places where this graph crosses the x-axis, okay, where y, or f of x, is equal to 0. All right, so I'm going to look at the graph, hit graph, and I'm going to do second calc 0, and I'm going to have to do this 3 times. Pick a point to the left, pick a point to the right, do my guess, and one place it crosses the x-axis is at -1. Okay, I'm going to do second calc 0. Okay, pick a point to the left, pick a point to the right, do my guess, crosses at 1/2. And the last place it's going to cross, second calc 0, pick a point to the left, pick a point right, and do my guess, is positive 2. Right, so those are the 3 places where it will cross the x-axis. Now, if we look back up at the equation we had factored, okay, watch what happens if you plug -1 into the first set of parentheses. You get -1 plus 1 is 0, and then 0 times anything would be 0. Well, let's look at what happens if you plug in 1/2 into the second parenthesis. 2 times 1/2 is 1. 1 take away 1 is 0. And then 0 times either of the other 2 factors would be 0. And the last one is 2. Plug that into the last factor. 2 minus 2 is 0. 0 times anything else in the other 2 factors will always be 0. So my point here is that if you can take an equation that looks kind of complicated like that, right, and then factor it so we get these sets of parentheses, you can find the zeros pretty easily by hand by looking at what makes each factor 0. If you can't factor it, that's when, if it's a quadratic, we could use quadratic formula. If it's a cubic or anything higher, we might have to rely on the graphing calculator for that. Right? So the 3 numbers that we just found, those are all called the x-intercepts. Right? They're the particular values that when you plug them in, make y 0. Okay? Another word for x-intercept, it's also known as a root or a 0. Okay? And if you're using a newer calculator, and you go second calc, you'll see the word 0. If you're using an older calculator, okay, like this TI-82, turn it on, you go second calc, they use the term root. Okay, so you could see either term, but if they're asking you to find a root or find a 0, what they want to know is what value do you plug in for x that would make y 0. Okay, for a linear equation, when we're trying to find a root or a 0, there's pretty much only one answer. Okay, unless you have a special case where you have a horizontal line, x equals 0. Okay, that would be a special case. But in general, any line that you draw can only cross the x-axis one time. Right? And here's how your solution would look. So if you've got an equation of the form ax plus b equals 0, and you want to solve for the root, you just subtract b, bring that to the other side, and divide by the coefficient of x, which in this case I represented by a. So it would be negative b divided by a. Right, so here's an example with this equation. Get minus 3 from both sides. Get 2x equals negative 3. And divide by 2. So x equals negative 3 halves. Okay, so negative 3 halves is the root of that equation. It's the number that if you plugged it in for x, it would make the equation come out to 0. Right? This is a quadratic type equation. Okay, the highest exponent is a 2. So from earlier, I said if you look at that highest exponent, it tells you how many times the graph could cross the x-axis. Okay, in this case, it could cross up to twice. All right? Could cross up to 2 times. So remember, we can use our discriminant to figure out how many times it actually does cross. Okay, so the discriminant is b squared minus 4ac. And what you do is fill in a, b, and c. If your discriminant comes out less than 0, okay, you're going to get a graph that doesn't cross at all. And that could look something like this. Doesn't cross the x-axis. If your discriminant comes out equal to 0, you're going to get a graph that just comes down, touches the axis, and goes back up. And lastly, if b squared minus 4ac comes out positive, that's when you get 2 x-intercepts. Okay, so using b squared minus 4ac, that's a quick method to just check how many roots you have, but it won't tell you where the roots are. Just tell you how many you have. All right, so let's try to solve this one. 2x squared equals 1 minus 2x. And they said to solve it approximately. Right? Anytime you want to solve a quadratic for its roots, whether you're going to factor, whether you're going to complete the square, most of the time we start by getting it equal to 0. So let's start by moving the 2x to the left by adding 2x and subtracting the 1. Now the reason I moved the 1 minus 2x to the left rather than moving the 2x squared to the right is because you generally want the coefficient of x squared positive. Okay, when you're trying to factor, use quadratic formula, anything like that. Okay, it just makes it a little easier, especially for factoring. Now this problem wouldn't factor, so one option we would have is to either complete the square or use quadratic formula. Okay, but let's try a graphing approach. So on my calculator, I'm going to type in, let's see, turn it on. We've got 2x squared plus 2x minus 1. Okay, do zoom 6. We'll see how that window looks. And it looks like it does cross in 2 spots. So we'll do second calc 0. Pick a point to the left, pick a point to the right, okay, do your guess, and we get about negative 1.366. And we're going to get one more answer. So do second calc 0, and we'll get this one on the other side. Pick a point to the left, right, and take a guess. It's about 0.366. Right, so those are the approximate roots for that equation. Those are the 2 values you could plug in for x, and it would make y come out to 0. All right, so I've already been showing you how to find the roots graphically, but what I want to show you is something in our book. They mention this older technique. Okay, you don't have to write this down. I just want you to just look at this part. Okay, before, on some older calculators, they didn't have the second calc feature, right? All they had was basically zooming. So if you wanted to find, say, this root right over here, we could go zoom 2, zoom in, and we could say, all right, we can see it a little bit closer. And then what they'd have to do is change their x scale. All right? And what this is basically going to do is put more tick marks on the screen. All right, so now looking at that, I can say, well, there's somewhere between 0.25, which is about right here, and 0.5, which is right there. That's where it crosses. All right? But if I wanted it a little more accurate, I could zoom in again. All right? And then I could set my tick marks even finer. So let's put a tick mark every 1/10 of a unit. And now I can tell you, all right, it's somewhere between 0.3 and 0.4. All right, so I'm narrowing down where the root is. And then I could repeat this, keep zooming in, making more tick marks on the screen. But this process takes a long time. Okay, and we don't want to have to find roots that way. So if you see in the book, it says find a root with a maximum error of like 0.01. All that means to do is round to 2 decimal places. Okay, we don't really have to worry about this maximum error because now we can find the roots this way. Right? We have a feature built in that does it for us. Okay, so I just want to make sure you're aware of that if you see that wording in the book about maximum error. All right, so let's try this one. X cubed plus 2x equals 1. Well, first thing we could do, we could treat this just like the other problem we did. Okay, we could start by getting it equal to 0. So we have x cubed plus 2x minus 1 equals 0. And we can graph it. And we're going to try to find where it crosses the x-axis. Now remember, take a look at that highest exponent. In this case, it's a 3. So that means this graph could cross the x-axis up to 3 times. Okay, let's hit graph. And you know what? We might want to adjust our zoom. Let's do zoom 6. All right, so this time the graph is going up. It's going up, going up, going up, and then right around in the middle it thinks about turning, but it actually doesn't turn, and it just keeps going up. All right, so we can see we've got one root. Let's do second calculate 0. Pick a point to the left, pick a point right, and do your guess. All right, so it looks like we get a root at about 0.453. So right there, 0.453. Now, another way you can do this problem, basically leaving it the way it's set up originally, rather than moving things from side to side, is take everything that's on the left, put that in y1. Take everything that's on the right, put that in y2. Okay, let me show you how this approach works. So we got x cubed plus 2x on the left, put that in y1. We got 1 on the right, we're going to put that in y2. And now we're basically trying to find where y1 and y2 are equal to each other. Well, where these two graphs are going to equal each other is where they cross. And they should cross at exactly the same spot we just had. So this time I'm going to do second calc, except I'm going to find an intersect. Okay, there's my first curve and my second curve. Do a guess, hit enter, and for the intersection, you can see we get exactly the same thing. The intersection is 0.453. All right, so which method that you want to use, that's up to you. I would say if you already have an equation equal to 0, it's easier to just type it all into y1, calculate a root or a 0. If you've got something on each side of the equation, maybe you don't want to rearrange it, just leave it the way it is. Put the left side in y1, put the right side in y2, and then just calculate an intercept. Right, so we've already been graphing some third-degree polynomials. Okay, a third-degree polynomial, in general, has the form ax cubed plus bx squared plus cx plus b. Okay, and in the last problem that we did, we had the cube term, but we didn't have this term. We didn't have the term with an exponent of 2. We did have a number with x, and then we had a number without a variable. Right, so you don't have to have all the terms, but if your highest exponent is a 3, then that makes it a cubic or third-degree polynomial. You can see on page 80 some of these pictures. In general, that's what a third-degree polynomial looks like. Okay, we've got the ones that keep going up all the time and never turn back on the left. And on the right, okay, we've got the ones that actually do kind of turn back on themselves. And these are the ones where you can get more than one root, or more than one x-intercept. Right, so let's just take a look at this equation and see how many solutions it has. All right, we already have an idea of a maximum number of solutions. Okay, look at that highest exponent. It's a 3. Okay, so it shouldn't have any more than 3 roots, or it can't. So let's graph it. So we get x cubed minus 5x squared. Whoops. Put in our minus 5x squared plus 6x minus 1. Okay, let's do zoom 6. And we're trying to find where this graph equals 0. Right. So it looks like it equals 0 in 3 spots. And actually, that's all I wanted to know here. How many solutions do we have? We have 3. Okay, the next question asks us to find the middle root. There's no significance for why they asked to find the middle one. It's not any more or less significant than the other 2. All right, so let's just practice finding it. So pick a point to the left, pick a point right, and do your guess. Okay, so it's about 1.555 if we round. So that's basically the idea of how you can find roots on the calculator. Keep in mind that sometimes you've got to change the window a little bit, especially if something goes off the screen, to make sure you're not missing a root. Right, and we'll finish up with section 2.2, just the first part. I don't think we'll get through the whole thing today, so we'll do what we can and we'll finish up next time. All right, so a lot of times when we're solving a mathematical problem, one of the first steps to do is to set up some kind of equation, all right, or to somehow represent our situation algebraically. Okay. Once we represent something algebraically, okay, then we have a couple choices about how we solve it. If you set up an equation, you might use algebra to solve it, or you might take that equation, plug it into a graphing calculator, and calculate some kind of root or 0 or intersect, okay, something like that. But almost all of the time, we have to set up an equation. And then some of the time, we'll use a graphical approach with that. Okay, on the one we do today, we're going to try both. Okay, we'll set up an algebraic equation, and then we'll use a graphical approach to solve it. Okay, in your book, this word problem is it's written out, but I've just kind of summarized the important points of what we really need for this problem. Okay, so it says Bill has $20,000 to invest. He's going to invest into 2 different investments. Okay, some of the money he's going to invest at 6.75% interest. The remainder, he's going to invest at 8.6% simple interest. Now, by them telling me simple interest, I know the formula that I should use. Okay, I don't expect you to know that because it's not something we've covered, so I will give that to you. Okay, there's your formula for simple interest. Okay, it's I equals PRT, where I is how much interest you make. P is the principal. Principal is how much money you're investing. R is the rate. And it's very important that we write the rate as a decimal. So for example, if it was 12%, we'd have to change that to 0.12. And T is the time. And for our problem, time will be measured in years. All right, so our goal here is to find an algebraic representation, or come up with an equation for how much money or how much interest Bill's going to earn in 1 year. Well, Bill's going to be earning interest from 2 different sources. He's going to earn some interest from this investment at 6.75%, and then he's going to earn some other interest from the investment at 8.6%. Right, so let's start by finding how much interest he earns separately in each of those investments. All right, so for our first one, interest at 6.75%. So interest equals. Okay, the first thing we need is the principal. How much money is Bill investing at 6.75%? Okay, I gave you a hint right here. Okay, assume that Bill is going to invest X dollars at 6.75%. So that's my principal. My rate, well, 6.75%. Make sure you change that to a decimal. So 0.0675 times my time. Interest equals principal times rate times time. In this case, I really don't even need the time because the time is just 1 year. But there's our interest, okay, at 6.75%. And we could write that how we normally do. Okay, when we have a number next to a letter, we usually put that in front. And there's our first amount of interest he's going to earn, okay, at the lower rate investment. All right, let's find out how much interest he's going to earn at 8.6%. All right, first thing we need here is the principal. Well, Bill had $20,000 to invest. He already invested X dollars. How much does he have left? Well, if he started with $20,000 and he's already invested X of it, for the other investment, he has $20,000 minus X. Okay, so if he invests $5,000 at 6.75%, that would leave him with $15,000 at 8.6. So there's my principal. Okay, my rate is 0.086. Again, my time is 1 year. Okay, what I would do here is, let's distribute this out and write it in a more standard form. So we've got, start with negative 0.086x. Okay, that's just rearranging a little bit. Plus 20,000 times 0.086 is 1720. Okay, so there's how much interest Bill earns in his other investment. Right, now I want to know the total. Well, think of it this way. If you worked and earned money from one job, and then you worked at another job and earned money there, you'd have two sources of income. And if you wanted to know the total, you'd take how much money you earned at your first job plus how much money you earned at your second job. Well, it's the same idea here. He's got two sources of interest. So we're going to take how much interest he earns from the first investment, which was 0.0675x, plus how much interest he earns at the second investment, negative 0.086x plus 1720, and that equals the total interest. Okay, the only thing we could do if we wanted, we could combine some like terms. So we've got 0.0675 minus 0.086. So that leaves me with negative 0.0185 x plus 1720. So if you wanted a little bit simpler, we could go with that. Okay, and there's an algebraic representation for the amount of interest that Bill will earn. Now, if we just look at that bottom equation, okay, let's just put it right there. Let's forget that this has to do with a word problem. Forget it's about interest and investing money. And you just wrote that on a piece of paper and showed it to somebody. If they looked at that equation, they would have no idea that there's a restriction on x. Okay, why would you? You can take and plug any number you want in for x and multiply by negative 0.0185. But if we tie this into our word problem, we have a little bit of knowledge about x. Okay, one thing is, we know that x can't be negative because that would represent investing a negative amount of money. Okay, and we can't do that. We also have an upper limit on x. Okay, x is the amount of money that Bill's investing. Well, Bill has a fixed amount of money. He only has $20,000 to invest. So it wouldn't make sense for x to go any higher than 20,000. All right, so what I'm trying to point out here is there's a difference between looking at an equation and graphing it in terms of just an algebraic equation without thinking about real life restrictions versus actually considering the restrictions we need to based on our word problem. Another example might be, let's say x represented the number of people that you were going to take to a concert. Well, x in that case wouldn't be a decimal. Okay, you can only take whole number of people to a concert. All right. So when you write an equation, keep in mind that there are restrictions on the values for x that you're allowed to use. All right, so using our graphing calculator, we're going to find out how much money did Bill invest at each investment if he made $1,509.10 in interest. Okay, well, this amount right here, that's my total amount of interest that I've made. So we're going to plug that in right there for the total amount of interest. So we have $1,509.10 and set it equal to our equation. Negative 0.0185x plus 1720. And I'm going to solve this one just like we did one of the last problems. I'm not going to rearrange it. I'm just going to fill in what's on the left side in y1. So it's 1,509.10. I'm going to put negative 0.0185x plus 1720 on y2. And remember we talked a little about the window. We're not going to have negative money to invest. We also can't invest more than $20,000. And right away, just looking at y2, okay, we have a y-intercept of 1720, and then the slope is negative. So it's going to head down from there. So I would set the y-max at least maybe 1800. That should give us a pretty good picture. Okay, so that blue line represents the 1509.10. That's a constant horizontal line. Okay, the red line represents the right-hand side of that equation. And we're going to see where they cross. That's where they're equal. So second calc intersect. Pick a point on the first curve. Pick a point on the second curve. And take a guess. Right, so the intersection is 11,400. So x is 11,400. Now, I just have to go back and remember what does x represent? X is the amount invested at 6.75%. All right, so Bill will invest 11,400 at 6.75. And since he has a total of 20,000 to invest, we take 11,400, subtract that from 20,000, and that leaves Bill with $8,600 to invest at 8.6%. Okay, so there's our answers. All right, last one we'll take a look at has to do with a problem I think we looked at in the homework one night, but take a look at it again. We're going to think about rectangles with a perimeter of 100, and I want to find an algebraic representation, or an equation, that describes the area of these rectangles in terms of their width. All right, first thing I would do, let's just draw a rectangle. And the perimeter is equal to 100. Keep in mind the goal. We're trying to find the area as a function of width. All right, well, there's my width. There's my width. So let's pretend we have 100 inches of material to build this rectangle. And we've used W on the left and we've used W on the right. So far we've used up 2W. That's how much material we've used up out of 100 inches. So we started with 100 inches and we've used up 2W. That's the amount of material we have left. But we got to take that amount of material and we got to build the top side of the rectangle and the bottom side, and both sides are the same length. So after we do 100 minus 2W, take that amount of material and divide it by 2, because half the material is going to build the top of the rectangle and the other half will build the bottom. So 100 divided by 2 leaves me with 50. 2w divided by 2 leaves me with w. So 50 minus w represents the length of this rectangle. Okay, now we're ready to write the area. Okay, we got to go back and remember the formula for area of a rectangle. Okay, area of a rectangle is length times width. So in my problem, the length is 50 minus w. That's length. And my width we represented by w. And there's a formula for the area of the rectangle. Last thing we're going to do with that formula is graph it and see what it looks like on the screen. Now, if you think about distributing this w out, you'd have a w times a negative w. That'd give me negative w squared. Okay? In this case, and also I'd have to distribute the w to the 50. So it'd be negative w squared plus 50w. That tells me that this is a parabola. Okay? So we're going to have that N-shaped look to this graph, or upside down U shape. But when you type it in, you don't even have to distribute it. Just leave it as 50 minus, in our case, we have to use x times x. Okay, let's look at our table. All right, we can see values up around 500, 600, 600. So maybe a good idea for the y max would be somewhere around 700. Y min 0, that's fine, because we're not going to have negative area. As far as x max, well, that's my width. Well, the width can't be any bigger than 50. Think about if you made the width 51. Well, then your width would be 51 on one side, 51 on the other side. That's 102 inches right there. Okay? You don't even have that much material. All right, so the biggest the width could be really is like 49.9, repeating. Okay, but we can't go any bigger than 49.9. All right, so let's look at this graph and see what we got. Okay, so that graph represents all the different areas. And you can see what happens if I let my width start to get really skinny. So I make a real long and skinny rectangle, like a width of 2. So that would be like 2 on one side, 2 on the other side. So I would have used up 2 units on one side, 2 units on the other side. That leaves 96 units, or 48 on each length. All right, so that's a long and skinny rectangle, 2 by 48. Doesn't give me that much area. In fact, if we go up to the maximum, okay, it'll show us the shape, or give us an idea of what shape would give us the best area. We can see x is about 25. Okay? In this case, we didn't have to find any kind of maximum area, but what this shows us is that if you let x be 25, right, that's your width, and you fill that into the formula for the length, which is 50 minus w, you get 50 minus 25, which is 25. So the idea here is that if you want to build a perimeter that's in the shape of a rectangle around something, and you want to use the least amount of material, but you want to enclose the most area, the best way to do it is to make your shape a square. All right? So that's a complete graph of our problem situation. All right, so the homework tonight is on page 82 and 88. Okay, 82, that's section 2.1. That's 1 through 5, 9 through 11, 15, 27, 28, 34, 40, 45. And page 88, that's what we started in section 2.2. That's numbers 5 through 12, 21 through 23, and 31 through 34. Keep in mind on page 82, I think in numbers 1 through 5, they are going to ask you to solve equations algebraically rather than graphically. So factoring could come up there. I don't think there's too many quadratic formulas, but factoring definitely does come up. So if you're a little rusty on how to solve something like this for zeros, Right? Just as a reminder, that's where you make two sets of parentheses. Okay, figure out what times what would give you the first term. In this case, my signs are both plus, and then what times what is 2, 1 and 2. And now, x equals -1 would make the first factor 0. X equals -2 would make the second factor 0. All right, so if you're a little bit rusty on the factoring, we'll take a look at that next time. Right, so this assignment will be due the next time I see you, which will be, let's see, October 5th.